Hello, and welcome back to another exciting episode of Machine Design. You may know me from my previous roles in Machine Design Lecture 15, Machine Design Lecture 16, Machine Design Lecture 12, and Machine Design Lecture 8. So, hopefully that's you recognize me, but if not, here's my name. It looks pretty. Thank you. Today we're going to be discussing bearings. So. Before we discuss bearings, I have a really important message for you. When it comes to most mechanical components, you will not be designing and building them. You will not be designing and building most of the bearings. In fact, if you try to build your own ball bearing, quite frankly, it won't work as well. The purpose of having bearings, the purpose of using bearings is not so that you go find a way to make it yourself. You use an existing one, okay? When it comes to machine design, if there is a component that satisfies your needs, that already exists, you don't have to design it. It becomes a selection problem, okay? Now, when it comes down to things like bearings, in general are regulated by the American Bearing Machining Organization, ABMA. I'm gonna make sure that that's right before I write it on the board. ABMA. ABMA. Really help if I spelled it right. Yeah, American Bearing Manufacturers Association. Okay, what does it mean to be regulated? Well, this goes into the idea of standards, okay? Every bearing is tested according to standards that are set forth by the ABMA, okay? The ABMA says you have to do a test using this type of a setup, using this loading condition, etc. It standardizes the tests. It's like issuing a standardized test to all students, but here it's just for bearings. And what these tests show is it gives consistent results such that if I buy a bearing from one company, if I go buy it from Grainger, it has a specific load rating on it, I can also go down to McMaster and buy a bearing with the same loading rating, and they will perform very similarly. Okay. The Bearing Manufacturers Association, ABMA, is in charge of ensuring the consistency and the quality of these items, okay? Otherwise, you can be like, well, I tested it at 3,000 pounds. Well, how did you test it? Did you make sure that it could handle that? You know, how did you test the viscosity of your bearing? All of these different factors. So every bearing has to be tested, and the standardized testing allows us to compare bearings and get some common knowledge. Otherwise, you'd have to be like, okay, well, if you're going to buy a bearing from Grainger, you have to use these set of calculations. If you're going to buy a bearing from McMaster, you're going to use these set of calculations. If you're going to build your own bearing, you're going to use these set of calculations. And it just becomes quite a very big headache. Instead, because they standardize the testing, we now can go look and say, all right, bearing loading rating, we got it for this bearing. we have this set of math that we can use because that math is given to you by the ABMA, which tells us how we can use the information that comes out of the testing. So that's really how it's needed. These same kind of testing standards are used for materials. It's why you have AISI 1020 steel. That rating, the testing that's performed on that, the material composition, the heat treatment that's done to it, everything that's done to it gives it this very similar set of properties to all kinds of 1020 steel, regardless of the manufacturer. So these associations are really necessary for dictating how these components are picked. So with that said, because we have the standardized testing that's already being done for all of these components, don't build them yourselves. You're going to use components that already exist, and you're going to plug them in to your design to make your design work. Okay? From here on out, when you're designing a bolt, when you're designing a spring, when you're designing bearings, you're choosing an existing component and plugging it into your design. You're even doing that with welding. You're doing that with materials. You're not going and forging your own metal here. Okay? We have standardized equipment, standardized materials, standardized components that we get to use for all of our designs. And for that reason, this isn't a design problem in that you're designing how to build a bearing. You can study how to build a bearing, that's fine. But if I'm going to give you the most useful information, it's not how to build a bearing, it's how to build with a bearing. Okay? So that's really where a lot of the machine design focuses now. How do you select components that already exist and plug them into your design to make them work? And this is how industry works. In industry, if an automotive industry needs a bearing, they will go look at the bearings that already exist on the market. If they don't like them, they will have to build their own. That's the way it is. If it's too expensive, they will have to build their own, and they have to abide by standards provided by the ABMA. So, I mean, you don't get around the ABMA that way. But usually what happens is they just buy bearings that already exist on the market, plug them in. That's what you do. Okay? So every bearing is tested by the ABMA. That gives it a lot of standardized quality. And the purpose of doing this is to have similar behavior between manufacturers. Gives everybody a bench line to work off of. Okay? So, when it comes to bearings, there are a number of different types of bearings that we can use. The reading assignment that I gave you for this week has two major components to your bearing design. One chapter 11, is on ball and roller bearings. And then chapter 12 is on journal bearings. Okay, and these are two very different kinds of bearings, have different purposes. So really, as we go in to discuss the concept of bearings, what they are or how to use them, I think the first thing we need to talk about is what's the difference between these two? All right, so you have, I'm going to go ahead and split this out into three. Ball bearings, roller bearings, and journal bearings. Okay. For ball bearings the whole purpose of, well, what a bearing is, if I were to define a bearing, is it allows relative rotation between components with minimal friction. That's the purpose of a bearing, okay? And in your car, you have bearings that act between the vehicle body and the vehicle axles, because the vehicle axles are spinning and the vehicle body is not. If your vehicle body is spinning and your axle is spinning, you're doing a rollover. Might get to work faster, but you will be hurt. So, the purpose of bearings is, you want a component to move relative to another component. This would be like anytime you have a revolute joint, okay? Anytime you have two linkages rotating next to each other. Quite frankly, in a 4-bar linkage, oftentimes you will have bearings put into your revolute joints. It's not just a simple dropping a bolt and that's it. Oftentimes there will be bearings involved, especially if there's loading conditions, but we'll talk about that in a bit. Okay, ball bearings, the way that ball bearings work are you have an inner sleeve that wraps around your shaft, and in that inner sleeve you have a ball, and then you have an outer sleeve, try to draw this right, that has a groove, and your ball bearing sits in between them and just rolls. It prevents the ball from falling out because of these two grooves. They're usually lubricated, etc., etc. And you'll have, so this is a cross section, you'll have a similar, here's your inside piece, your ball bearing, and your outside piece again. And your outside piece is, that's one continuous circle. Your inside piece, that's one continuous circle. You stick your shaft into this circle. This piece spins at the same speed as your shaft. This piece spins at the same speed as whatever other object it's mounted to. Okay, so like if this was a vehicle, then this would be mounted to the vehicle and this would be mounted to the axle. And here then this would be the axle as the axle spins. Okay, a ball bearing is rotated about half the speed. One revolution of this, I think you end up having, you don't have anywhere near one full revolution of the ball bearings, just because that's how the ball bearings are rolling inside of there. Roller bearings are a little different because they're built differently. You can have tapered roller bearings, you can have needle roller bearings. I'm going to show just needle roller bearings here as a result. So a needle roller bearing, you have a very, very thin roller. It's in some kind of housing like this, and this may either, sometimes I've seen it where the needle bearing has some kind of pin that holds it in place, and then the needle will directly contact whatever axle it's on. Sometimes you'll have this rolling relative to another component, a sleeve or something that fits onto the axle. But in any case, the roller bearings have cylindrical or tapered rollers. They're not balls. They're very similar. These have a lot of the same qualities. It'd be like you could use this as a needle bearing. If my hand was some kind of a cup and I had an axle in here that's rotating, this marker would act as a needle bearing because it's just long and thin. It doesn't rotate 360 degrees. It just rolls very nice and smooth. Okay, journal bearings are a little different. In both of these systems, you have a mechanical component that rotates, and the rotation of that mechanical component really transfers the energy. Okay, this rolls because it has a ball bearing that rolls. This rolls because it has a really long, thin roller that rolls. In a journal bearing, you don't have any of this. What you have is you have a bushing. Here's your axle, and your bushing goes all the way around, and your bushing would be directly mounted to whatever component is holding this, like such as the vehicle. And in between the bushing and the axle, the way that this works is that this axle moves relative to the bushing. It rotates inside of the bushing. So if this was my axle, my hand would be my bushing, it just spins relative. And what they do is they add in some kind of a lubricant in here, such as oil or grease, something. There's a lot of different kinds of lubricants that can be used in a journal bearing. In a journal bearing, you do not have the rotating parts of a ball bearing or a roller bearing. In a journal bearing, your relative movement occurs through a fluid. And there's a lot of interesting theory behind how they actually move. But this is ultimately it. You have some fluid, and the fluid movement, this is what provides resistance. Here, what provides resistance is the friction between the ball bearing and the other joint, and the friction between the ball bearing and the lubricant that's used. And similarly here, it's the friction between the roller bearing and the joint, and also the friction between the lubricant that's being used. So these are the three different types. Now comparing, the ball bearing can handle axial loads. Okay, what is an axial load? Well, it's what happens if I were to take this axle and I was to exert a force in this direction. You know, if this is the axle that's spinning, or my shaft that's spinning, and my hand is the bearing, and I were to push on this axle in this direction, that's called it's an axial load or a thrust load. Okay, this can handle thrust loads. It can. This can't handle it as well. The thing about thrust loads is that this holds the ball bearing. The ball bearing is held relative, so it can't move. In this one, these don't really hold thrust loading as well. In fact, sometimes you want this to slip in thrust. Sometimes that happens. You can design a roller bearing to be able to handle it, but usually those tend to be a lot more expensive. If you're going to be able to handle axial loads, usually you go with a ball bearing. Okay, journal bearings can't handle thrust load at all. Okay, this fluid doesn't like, oh no, it's moving quickly, resist. It doesn't do that. Okay, if you're moving this shaft at all, it just slides inside the journal bearing. This can be nice for that reason, because sometimes you don't want there to be axial resistance, which is great. But sometimes you do. So yeah, that's these three. All three of these can handle radial loads. Okay, what is a radial load? Well, a radial load is a load in this direction. It's pointed towards the center line of the axis of that shaft. You know, you can imagine that you have a vehicle that's sitting on an axle. It's exerting a radial load through these bearings, because it's loading vertically relative to these bearings. That's how your vehicle sits on its axles, is through that radial load. All three of these can handle radial loads. In fact, that's really one of the major things about this. Bearings do not provide a torque load. The torque that's created is caused by friction inside of these members, where the bearings do heat up, which that does happen. But the idea is you want that friction to be minimized, because you don't want there to be any energy losses inside of your bearings. So we treat it as if there is no actual torque created by the bearing, but in reality there is a small amount of torque, and that torque is due to the losses of the ball bearings rolling, the losses of the roller bearings rolling, the losses caused by the fluid heating up in a journal bearing. Okay, so all of these can handle the radial load, all of them can handle something sitting on it while it spins. Depending on your application, you can design a journal bearing to have the least resistance, the least friction. Okay, this is why for a lot of automotive applications where there are a lot of revolutions, they will use journal bearings instead of using ball bearings. Okay, ball bearings can heat up a lot. Now this isn't a super high friction thing, but it's not something where you're like, oh, ball bearings, gross, it's tons of friction. But the friction here is substantially larger than this. And the same for roller bearings. Although roller bearings tend to have less friction than a ball bearing. But it still has the more friction than a well-designed journal bearing. So keep in mind that this progression here, if you need something that can handle axial loads, you're usually going with ball bearings. If you need something that doesn't need to have an axial load or a thrust load, and you want to minimize the friction, which usually you want to minimize the friction, then you go with a journal bearing. If you want to go with something that, oh, I should say this, these can be designed to be permanently lubricated, okay? And these too. Now, sometimes you may see a bearing that has a nipple on it. Yes, that is the scientific word for it. And all that is it's a little spout here that you plug in that you use to add lubricant to the bearing. If your bearing for some reason is drying out or the friction is increasing, adding a little bit of lubricant through the nipple, it's good for it. Okay. Similarly, you may have nipples on roller bearings, and you may also have nipples on journal bearings, which is not something you probably expected to hear when you signed up for class. We'd be talking about nipples on bearings, but that's what it is. That's how you put more lubrication into the bearing, and usually you can tell whether or not usually you can tell whether or not it's going to need more lubrication based on the amount of friction that's provided. Now, most journal bearings will require additional lubrication. Okay, it's just the nature of it. You have sliding components, etc., etc. Well-designed journal bearings in systems where you do not have a whole lot of axial motion sometimes will not require any lubrication at all. That's why you don't really go in and have to lube up your wheel axles. Even though there are journal bearings in there. They're well-designed bearings, but in most applications, anytime you have a journal bearing, you really usually have to do it. There are some ball bearings that are fully shielded. Shielded prevents dust from getting in, but also prevents the lubrication from getting out. And those can be permanently lubricated, no problem, last forever. You can do the same thing with roller bearings too. So if it's an issue where you absolutely do not have the ability to go in and lubricate that, that's another case for ball bearings. Although again, you can get journal bearings where you don't have to provide additional lubrication. And a lot of times the way that you apply additional lubrication is through actually having some kind of a nipple on the outside of your bearing. So That's the difference between these three different types. Now we're gonna very briefly discuss what it means to, if you have a bearing and you have some loading on it, how do you design that bearing? Now with ball bearings, what you end up with is all ball bearings have a reliability rating given to them that's called the L10. Okay, so ball and roller bearings. What the L10 rating is for a bearing is the 90% reliability for a certain speed, for a certain amount of rotations. Okay, so how much load would mean that 90% of the bearings would survive at that loading for that number of rotations. Okay, it's really hard to guarantee 100% of the bearings will always survive, because you never know when you're gonna have a ball bearing that just goes whack. They're very limited, but it does happen. Ball bearings can have small deformities in them with increased fatigue loading that's caused by the rolling motions. It can cause the ball bearing to crack in half. As soon as that happens, it fractures and fragments pieces of ball bearing all through the lubricant throughout the ball bearing joint, and it just mucks everything up, and eventually the bearing is just shot. Okay, sometimes that happens. So 10% of the bearings will experience some failure like that, but 90% of them will be fine at this loading for this number of rotations. Okay, and you'll end up with an L10 curve where your L10 curve, your L10 value for your load versus your number of cycles ends up going something like this. Okay, so at lower cycles it can handle higher loads. At higher cycles it can't handle as much loads, and this is the case. Now if you wanted an LO5, which would be a 5% loading cycle, which most manufacturers don't give, that does tend to be lower then. Okay, because you can't expect as much out of 95% of the population of bearings. Similarly, if you're going for an L50, where 50% of them fail, then it's much higher. No, that doesn't tell you a whole lot, unfortunately. So oftentimes what is used is we do focus on this L10 rating. There are methods in the book for calculating it at different reliabilities. That is a little bit in your reading assignment. You can read through that in your spare time. We're not going to talk about it in this class just because I want to focus on the fundamentals here. The way that L10 is calculated is they calculate C over P to the E times 10 to the 6th divided by 60 times N. Now what do all these variables mean? Well, this is your L10 life. This is the 90% reliability load rating. C is your dynamic capacity. It's probably in pounds. P is your equivalent bearing load. Also in pounds. E, this is your, well, it's for ball bearings. It's 3.0 for ball bearings. And this is 10/3 for roller bearings. And then we have N is the rotation speed. Okay. And this is in RPM, usually. Okay, so being able to do this, what we figure out is you can use this value. Basically, if you have an L10 rating for a component and you want to change what the change what the equivalent bearing load is on that bearing, you change the p-value with a given L10 value for that bearing. It'll tell you how much load it can actually handle. Okay, so usually you're altering this and this simultaneously. This is your value that you change to get here. Okay. So that's really what you're looking at. And you do have to pick, okay, how long do you want your bearings to survive if it's a ball bearing? If you want it to go through 10 million cycles, your N is going to have some life of 10 million cycles at some certain speed. Are you looking at a nominal speed of, if you're going down the roadway, is it 30 rotations per minute, or are you looking at 120 rotations per minute? What is that speed that you're dealing with? Okay, so this is one way to do it. There are a couple examples of how to do this in the book. The book uses a different formula. You can follow the examples in the book. But what I'm going to do now is I'm going to go ahead and talk about how to select a bearing for an application. And I am going to focus a little bit more on ball bearings. I mean, I guess I could do another example with journal bearings later this week. I'll consider that because I think journal bearings are important and they're really useful. Journal bearings are very common. You can't, just because ball bearings have so much information about them doesn't mean journal bearings aren't significantly useful also. But so I will be posting a video. My next video will be on selection of a ball bearing joint, and we'll move from there.